Okay, today we're going to be looking at derivatives and gradient functions. This is going to be an introduction into differentiation. So we're going to be thinking about, to begin with, what is a derivative? So let's consider a curve, a general curve of y equals x squared. So we're going to consider a point on that. Consider point P with gradient x. Now the y coordinate would be x squared. So let's draw our curve. So we've got it coming around here, and this is our point P, x, y, but y is equal to x squared. So this is point P. Now we're going to consider a point A very close to P. Now I'm going to do it over here, and it doesn't look like it's close to P, but that I'll just kind of exaggerate. But in reality, these points are meant to be really close together, and it deviates from point P by x coordinate, and it's going to be we're going to do a very small deviation, and in the y coordinate by a small deviation in the y coordinate. So the coordinates of A are x plus this little thing dx and y plus dy, which we can also write that as x plus dx squared and x squared, or not meant to be squared. X squared plus dx squared. Now if we think of the gradient of a chord PA, so a line here PA, so P and A are so close together, the curve in this the curvature of x squared doesn't make any difference. So the chord would be a straight line. The gradient of PA would be y2 minus y1 over x2 minus x1, and we can put these in, so that's going to be x plus dx squared minus x squared over x plus dx minus x. Now we can multiply this out, so we get just do that properly here. Multiply that out, so we get x squared plus 2x dx plus dx squared minus x squared over dx, and that will give us 2x dx plus dx squared over dx, which is, we can take dx out here, so we get 2x plus dx. Now as dx tends to 0, so these points P and A get closer and closer and closer together, as dx tends towards 0, A tends towards P, and the gradient of PA gives the gradient of the curve at point P, which in this case would be equal to 2x. The process of finding the gradient of curve is called differentiation, and this process of finding differentiating functions by looking at the gradients of the chords is called differentiation from first principles. Now, although this isn't examined in the A-level course, so you won't have a question like this, it's important to understand the principle, because this is a principle that underpins differentiation. So when we differentiate a function, what we're actually doing is finding the equation that will give us the gradient of that function at whatever point we want on that curve. So let's think about some of the notation. So there's different ways that we can write notate differentiation. So let's think about whether y equals x squared. So we can then say dy by dx equals 2x. Or we can say if we've got some function f of x, again equals x squared, the derivative would be f dashed of x equals 2x. So the dy by dx and f dashed of x mean the same things. This is the derivatives. And we can also have d by dx x squared equals 2x. So that means we are differentiating this function on the value of x. So if this comes in useful, this notation comes in useful when you have a function with different variables and you want to differentiate it but with respect to one of those variables. Now, let's consider some power functions. So we've already done x squared, so what if we have d by dx of x cubed? Well, that would be 3x squared. And d by dx of x to the power 4 would be 4x cubed. And d by dx x to the power 5 would be 5x to the power 4. So we can see this gives us a general rule. D by dx x to the power n, the derivative is n x n minus 1 for any real power of n. And so we can think the rule would be multiply by the power n and then subtract 1 from the power. So we're going to do some examples. So we've got x to the power 7, 1 over x squared, and we've got f of x is the square root of x, and y equals 2. So d by dx of x to the power 7 would be, we multiply by the power, so 7 x, and then 7 minus 1 is 6. Now this here, d by dx or 1 over x squared. Well, we can rewrite that as d by dx x to the minus 2, and we can do it the same way. So we'd multiply by the power, so it's going to be minus 2 x minus 1 minus 1 is going to be minus 3, and then we would rewrite it in this form, so it would be minus 2 over x cubed. Now for f of x equals to square root of x, well, that equals x to the power half. So f dashed of x would be, so we multiply by the power, so it's going to be a half x. Half minus 1 is minus a half. Minus a half. And then we'd rewrite it in this form, because we'd then have our 2 down here, and that would be square root of x. And finally, for y equals 2, well, y equals 2 is the same as saying 2x to the power 0. So that would then give us 2 times 0 times x to the minus 1, 0 minus 1 is minus 1, but then that's a 0, so it just equals 0. So whenever you've got a constant, it equals 0. So we're going to look at some more general rules. So if we've got a scalar multiplying our function, so for what I mean by that is d by dx of k f of x, we can take the scalar out and then just multiply our function as normal. And if we have, I'm going to find d by dx for some function f of x plus or minus g of x, that's the same as saying f of x for the function f d by dx, the derivative of f of x plus or minus d of x for g of x. And this will become clear when we do some examples. So we're going to differentiate (3x to the power 4 minus 1 over 2x squared plus 4 gx plus 5 with respect to x. Now this is actually like what we have here. We can think of each one of the parts of this function as little functions all added together. So we'll go d by dx 3x power 4 minus 2x squared plus 4 over root square root of x plus 5 is equal to, now we're going to rewrite these d by dx of, so we're just going to leave that 3x to the power 4 minus, that is a half x to the minus 2 plus 4 x to the minus half plus 5. Now we can differentiate it. So the first part we're going to have, so this one here, 3 times x to the power 4, is like we have what we have here. So we just, the 3 just sits here, and it's going to, the power is going to multiply the function. So we have 3 times 4 is 12, x, and 4 minus 1 is 3. So here we have minus a half minus 2 x, so it's going to be minus 2 minus 1 minus 3 plus 4 times a half x minus 1 minus a half minus 1 is going to be minus 3 over 2 plus, and that's going to be like saying 5, that's like saying x to 0 here. 5 times 0 times x to minus 1, which is going to end up being 0. So we've got our 12x cubed, that's going to become a positive, and it'll be 1 over x to the power 3, because those will cancel, minus 2, I will have the over x cubed, because that's, say, x to the 3 over 2 is the same as cubed, and this will just be 0. So that's our answer for this one. Let's do a couple more. So we want to find the gradient of the tangent to the curve y equals x, 2x minus 1, x plus 3 at point 1, 4. So we're going to, so remember, if we want to find the gradient, we need to find the derivative of the curve. So dy, so first of all, we've got y equals x, 2x minus 1, x plus 3. So we need to multiply this out. So we'll leave the x there, so it's going to be 2x squared plus 6x minus 1x, which is 5x minus 3. So that's going to give us 2x cubed plus 5x squared minus 3x. Then dy by dx is going to be 3 times 2 is 6x squared plus 10x minus 3. Now we want to find the gradient at point 1, 4. So we're going to substitute for when x equals 1, dy by dx will be 6 times 1 squared plus 10 times 1 minus 3, which will give us 13. So the gradient is 13 at point 1, 4. Final example, the curve y equals ax to the power 4 plus bx squared plus x has gradient 3 when x equals 1 and gradient minus 51 when x equals minus 2. Find A and B. So we're going to find, first of all, we're going to find the derivative. dy by dx will be 4ax cubed plus 2bx plus 1. So that, when it's just x, the gradient will be 1. So when x equals 1, dy by dx equals 3. So we're going to, so that means 4a, that's 1, plus 2b plus 1 equals 3, and when x equals minus 1, dy by dx equals minus 51. So we will have 4a minus 2 cubed plus 2b minus 2 plus 1 equals minus 51, which is minus 32a minus 4b equals, bring that over here, minus 52. So let's rearrange this one. 4a plus 2b equals 2. So this is going to be equation 1, and this is going to be equation 2. So equation 2 minus equation 1, just going to solve it as simultaneous equations, gives us 6a equals 12. So a must be 2, and then substitute a equals 2 into equation 1. So that would give us 4 plus b equals 1. So b must be minus 3. So I hope that helps.